For the EM spectrum and electronic transitions activity, we begin by looking at light, or electromagnetic radiation. The electromagnetic spectrum is very wide. It varies from high energy gamma rays to very low energy radio waves. And in between, we have X-rays, UV, visible light, IR light, microwave radiation, and visible light, of course, that's what we see by. So light, or electromagnetic radiation, has many properties to it. Two big ones are that it can be thought of as particle-like. It can be thought of as wave-like. As a wave, it moves with like a sinusoidal wave as it propagates through space. It propagates at the speed of light, c, which is 2.998 times 10 to the 8th meters per second. We see that in the equation 1. And as a wave, it has a wavelength. We often symbolize wavelength with the Greek symbol lambda. It has a frequency. We often abbreviate that with the Greek symbol nu, looks kind of like a V. Wavelength is the length of one cycle. Frequency is the number of cycles per second. Very short wavelength electromagnetic radiation is the very high energy light. Short wavelength means high frequency and means high energy. Amplitude is the height of the wave, as you see in the diagram. There's a relationship between wavelength and frequency, and you see it in equation 1. Their product is c, the speed of light. The energy associated with electromagnetic radiation is given by E equals h nu, where h is a constant, 6.626 times 10 to the minus 34 joules seconds. It's called Planck's constant. The energy is also equal to hc over lambda. That's probably the form of the equation I more commonly use, E equals hc over lambda. In this figure 2, we see the energy spectrum from the very high energy, high frequency, short wavelength end, the gamma ray end. By the way, gamma rays are associated with nuclear reactions, so they're very high energy. We see their frequency around 10 to the 21 hertz. Hertz is 1 over second, so it's a cycles per second unit. Very short wavelength, 10 to the minus 4 nanometers. Then we have next X-rays. You've probably all had an X-ray of your teeth. Then we have ultraviolet radiation. That's coming to us from the sun. That's what burns our skin, is hard on our eyes. Then we have the visible spectrum. That's what we see by. Remember that we remember the order of it from Roy G. Biv. The visible spectrum varies from about 400 nanometers at the very high energy violet end to 700 nanometers at the low energy red end. Next, we have infrared radiation that also, as does the visible, as does the UV light, come to us from the sun. And it is what warms us. We don't see by it, but we perceive it in that it feels warm to us. Next in energy, we have microwave radiation. You probably have warmed food in the microwave oven. And lastly, we have the low energy, low frequency, long wavelength radio waves. So we see the frequency ranges, and we see wavelength ranges, which you'll need to refer to for one of the future questions. Alrighty, so our next section has to do with line spectra, and we're using the Bohr model when we talk about hydrogen, which primarily is what we talk about. So we see in figure 3, on the leftmost side, the hydrogen emission spectrum. That one has 3 lines, 2 violet lines, a blue-green line, and a red line. Now think of the energy order. Violet, that's the high energy and short wavelength N. So the violet lines are the highest energy ones. And then the red line is the lowest energy line. We see the neon emission spectrum, and it is very different from the hydrogen emission spectrum. The mercury emission spectrum, we see that it is different yet. Each element has its own characteristic spectrum. Many scientists have worked with hydrogen and the emission spectrum of hydrogen. So scientists were able to measure the wavelengths of those 4 lines. They've even worked with other lines in the hydrogen emission spectrum, just outside of the visible spectrum. The visible spectrum has only those 4 lines, but there's the lower energy IRN, there's the higher energy UVN. We just don't see them with our naked eye. We can measure them and work with them, but we need a spectrometer. Okay, so a couple of scientists who worked with hydrogen were Balmer and Rydberg, and they had the wavelengths of those 4 lines and came up with this equation 3 that is a relationship between wavelength, lambda, and a term n. We see in their equation a constant r sub h, the Rydberg constant. We see its value 1.097 times 10 to the 7 inverse meter. We also see that n varies from 3 to 4 to 5 to 6 and so on. It's always greater than 2. R sub h is not r, the universal gas constant. Bohr was another scientist who worked with the hydrogen spectrum, and he came up with what we call the Bohr model, where he said that we see those different lines because the electron, remember that hydrogen has 1 proton and 1 electron, the electron can be pumped from its low energy state, the ground state, to a higher energy state by some sort of energy, and then it falls back down. As it falls back down, it gives off light. So he came up with a model for those different energy states. The lowest energy state, what we call the ground state, is symbolized n equals 1. So in the diagram here, figure 4, for the Bohr model, you see it's an orbit about the nucleus being the black dot in the center. So when the electron's in the n equals 1 orbit, it's in the ground state. It can be in 2 or 3 or 4 or wherever. We're seeing in our diagram there levels from 1 through 6, but it goes on up to infinity. When the electron is in n equals infinity, then it's basically removed from the atom. We would say it's ionized. So we also see an energy level diagram showing the lowest energy state, the ground state, n equals 1. Then we see n equals 2, 3, 4, 5, and 6. There's, of course, many between n equals 6 and n equals infinity. They're just not shown in the diagram. So when the electron's in n equals 1, it's in the lowest energy state. All the other states are referred to as excited states. Bohr came up with this equation 5 for the energy of the electron given the state that it's in. So E, the energy of the electron, equals to negative 2.178 times 10 to the minus 18 joules times 1 over n squared. So depending on what n state the electron's in, we can calculate its energy. Now, electrons, let's go back to our diagram. Electrons can be pumped up by some kind of energy like electrical energy from n equals 1 to some higher energy state. So we would picture that as a transition with like an upward arrow going from n equals 1 to something like perhaps n equals 4. Well, the electron will not stay in n equals 4 very long. It will transition back down to maybe n equals 3, or maybe n equals 2, or maybe all the way to n equals 1, and it will give off an electron. It will give off a photon of light as it makes that transition. If the energy gap, the delta E, the energy gap, is corresponding to energy to the energy of light, to light energy in the visible spectrum, we see that light. That's one of those 4 transitions. So Bohr's other equation, equation 6, describes the transition energy of the electron. So delta E would be the energy gap when an electron makes a transition up, arrow up, if energy is absorbed by the atom, or makes a transition down, arrow down, if energy is given off by the atom. So that delta E equation is negative 2.178 times 10 to the minus 18 joules times 1 over n final squared minus 1 over n initial squared. So if we have those n final and initial values, we can calculate the energy involved in that transition. That equation here is this equation 6 is the energy change associated with the atom. Well, energy is given off in the form of light, so that delta E of the electron is equal to the energy of the photon, which is hc over lambda, where lambda corresponds to the wavelength of the light that has been generated. So we can come up with equation 7 from equation 6 just by doing a little bit of rearranging with the C and the H that are part of the photon energy equation, and come up with this equation 7. So n low, n high correspond to this n final and initial. This figure 4 shows various transitions. Now, these all have downward arrows. What that means is the electron has been pumped from n equals 1 to some high energy state using some kind of energy, usually electrical energy. So if it's pumped up to the n equals 2 state, it's there for a moment, and then it falls back down to n equals 1. That would be the leftmost line shown on this diagram. So we have different series named after different people who studied them. The Lyman series, notice that they all end in n equals 1. The Balmer series, n equals 2. 4 of those lines in the Balmer series are in the visible spectrum. The 3 to 2 transition, that's the red line. The 4 to 2 transition, that's the blue-green line. The 5 to 2 transition is one of the violet lines, and the 6 to 2 transition is the other violet line. Notice that the arrow for the red line, so the leftmost one in the Balmer series, that is the shortest length, the shortest arrow length. That would be the lowest energy. That's the red line. Count over 3, you get to the 6 to 2 transition. That's the longest arrow. That's the highest energy transition in the Balmer series that we can see in the visible spectrum. So the length of the arrow has to do with the delta E, and keep in mind that short wavelength corresponds to high energy, long wavelength, low energy. Okay, so that's our introduction. You can skip the pre-activity. And we've got then the report. So in the first part of the report, you would be actually doing something if you were in the lab. We have that information in Canvas. So take a look at it, and then the observation just draws some kind of a picture of what incandescent light looks like when we're using a diffraction grating to break it up into its individual components. LED looks a lot like the incandescent white light spectrum, but it favors some wavelengths over others. The neon lamp, well, I give you a diagram for that, but frankly, in this introduction, there's also the diagram. So anyway, do the best you can to draw what those spectra look like in the observation area. So next, you would be using a hydrogen discharge lamp to look at the hydrogen emission spectrum. So that is the one basically that is shown in the introduction. And what isn't shown in the introduction is what the values are for those actual wavelengths. So I show you that in Canvas, so look at that so that you can write down what the wavelength of each line is. So you're doing that for the violet line, line 1, the other violet line, line 2, the blue-green line, line 3, and then the red line, line 4. And those are in units of nanometers. And then in this diagram 3, what you're showing is what is the source, what is the energy change that occurs in the atom that accounts for each line. So here we have those arrows going down. Remember, the longer the arrow, the higher the energy. And also remember that high energy means short wavelength. So you indicate in the boxes lines 1, 2, 3, and 4. And this question here is the n equals 7 to n equals 2 is one of the lines that would be occurring if we pumped an electron in an atom up to n equals 7, it falls back down to n equals 2. That's a transition that occurs. We don't see it in the visible spectrum. Why not? So calculate the delta E associated with that. Get the wavelength that would be associated with that for the photon given off. Is it in the visible spectrum? Okay, and then you're making some calculations going from frequency to wavelength. Here we have a wavelength. You're calculating the energy of that light. You're answering a question about comparison energies, wavelengths, frequencies. All right, now we're looking at electronic transitions in part C. So we're using the Bohr model, and we have an energy level diagram showing transitions A through F. You're deciding which are ones that correspond to energy absorbed, which are ones corresponding to energy emitted. So think about the direction of the arrows. And you then are ranking the transitions in order of increasing absolute energy change. So that just has to do with the length of that arrow, whether up or down. And problem 9, hydrogen atom in the n equals 4 state, and then you're calculating the wavelength associated with the 4 to 2 transition, and you're answering question B as well. Now you have in question 10, n equals 6, and making another calculation, drawing arrows, and so on. Actually, you don't need to make a calculation for 10, you just need to draw arrows answering the question. Question 11, so that refers to the series that we saw on page 210 of the introduction, those 3 different series. And so take a look at those and answer these questions. And keep in mind how the length of the arrow corresponds to energy. How does wavelength correspond to energy of light? All right, and then we're number 12, calculating a delta E for the 3 to 1 electronic transition in hydrogen. And lastly, we have question 13, which is having us show what it means for the atom, the hydrogen atom, to be ionized, to completely lose that electron. So it goes from the ground state up to where to be completely disassociated from the atom. And then you're calculating the energy corresponding to that transition. So of course you're going to have an energy, an arrow up, and you are going to then calculate delta E associated with that transition. That's it for this report, so make sure you're happy with your answers and scan your report as a PDF file and then submit it.